Hi, Henry. What's that?
Oh, it's an encoder.
Oh! All right, Henry, I assume these are encoders?
They are encoders. They're used for position feedback.
Okay.
So what you do usually is you take the shaft of the encoder and you connect it to something that is, in this case, rotating, and it allows you to tell where in the rotation that object is.
Okay, so is it like a sensor?
Yeah, it's a really advanced sensor.
Oh.
Yeah. They're used to tell some sort of control device where a rotary mechanism is.
Well, I don't know anything about them, so could you please explain the differences in these encoders?
Sure. I think let me start by explaining the general principles of how encoders work.
Okay.
So I have one here that I think we can take apart. There we go.
Ooh.
So we can get inside this guy, and it's got these screws here. So now that I've got those screws off, you can sort of see what's going on underneath the circuitry.
Well, I can see it, but I have no idea what's going on.
Fair enough. So there's this little disc. Do you see that disc?
I
there?
do.
So that disc is connected to the shaft of the encoder, and so in this particular case, this is a hollow shaft encoder, so there's actually going to be a shaft that goes into this one, and then there's a coupling that will clamp onto the shaft and, you know, capture it, right? There's other encoders like this guy. He's got a solid output shaft, so this is a solid output, and the one I'm looking at now is a hollow shaft encoder. So, but they all generally have the same operating principle.
Okay.
They all have this little mechanical disc inside that is attached to the rotary mechanism, and that disc goes round and round and round, and it has an etching in the disc. I don't know if you can see those lines in there or not, but
is it like a record?
it's similar to that, yeah. So this particular one is pretty close to like a DVD or a record or a CD, right? So I've got a reader on the circuitry, right? And a light source underneath it. And so as those etchings on the disc go around and round, it communicates an electrical signal. You know, this is an optical system, right? So it's basically converting optical pulses into an electronic signal, and then it can send those signals to these wires and send it to a controller of some kind.
Is this sensor underneath here, is it looking at different levels of light, or is it like a 1 and 0?
So it'll basically be like a 1 or a 0.
Okay.
Right.
Okay.
So this encoder here is what you would call an incremental encoder.
Uh-huh.
So what that means is that there is a series of pulses that are going to be sent through these wires to a controller of some kind. The controller will count up the number of pulses as they're coming in, and it can determine what the position is by counting the number of pulses. So let me stick this back together because I've got my sticker cut in half here. There we go. So you can see there it says 1024 PPR. Right? So that would be 1,024 pulses per revolution. When I get to 1,024, I know I've gone 1 revolution. If I get to double that, I know I've got 2 revolutions. And if I get half of that, I've gone half a revolution, right?
Okay.
So you can do the math to figure out where you are. And then in this particular case, this is actually a pretty high quality encoder. This one is actually able to tell the processor if I've gone forward or reverse. So there's 2 sets of pulses now. That's why there's so many different wires. Okay. It's not just one set of pulses. There's one for telling if I've gone forward, one for telling if I'm going in the reverse direction. So then you can start adding pulses and subtracting. If I go forward, I add pulses. If I go backward, I remove the pulses.
So this is a incremental encoder. There was an absolute encoder also?
That's right. So incremental encoder, and then we have an absolute encoder. This one's also an absolute encoder off of the back of a servo motor.
All right, what's the difference here?
The main difference is what happens during a power cycle. With the incremental style encoder, you're adding pulses and subtracting pulses. When you turn off the system, you lose that count, and you have no way of knowing where you are on the encoder disk anymore. So you have to do something called homing, so that when you start up the system at the beginning, you're starting at a specific point and you're telling the controller where you are, and then you can start counting from that point. With an absolute style encoder, there is even more specialized mechanical systems inside of these that allow you to know where you are even through a power cycle. So there's an etched disk, another specialized etched disk inside of this style of encoder that it basically has a unique address for each position all the way around. As you rotate that shaft of the encoder can always tell you exactly where it is, because if you think about it, every maybe you call it a degree mark, every degree has a specific address, for lack of a better term. So this one is different from this one, is different from this one, right? So you're always able to tell the controller where it is, and you don't necessarily need to home every time you have a power cycle. Absolute encoders have some sort of communications technology built into them. You can see this is an absolute encoder. There's only like 4 wires coming out of it.
Yeah.
So that's a lot simpler than this incremental encoder that has several wires coming out of it. That's because there's a lot more computational processing happening inside of this encoder, and then those signals, that information is being sent to the controller via some sort of communications. This is what Rockwell Automation calls DSL feedback, so digital servo link. It's a specialized proprietary communications that Rockwell uses. This encoder here is an Ethernet IP encoder. So you can communicate with a controller over Ethernet, just standard unmodified network communications.
Why would you use one or the other in what environments?
Yeah, so it really comes down to application requirements, right? So let's say I've got a system with 100 servo motors on it, and they're all in very specific spots in the machine. They're all aligned, and maybe they're interdependent, right? So if I can't move one without the other, right? If I have a power cycle in that situation and I have an incremental encoder system, I'm gonna have to rehome everything, and that process can take a long time. So that would be a system in which you would want to spend a little bit more money so that you don't have to waste money after the fact when you're actually running your equipment.
Okay. Do you have like an example of like where I could use an incremental?
Something like a conveyor belt. So if I need to know where a conveyor is, let's say I'm moving this encoder, for example, and I'm moving this encoder and I need to know where it is on the conveyor belt so that, let's say, a robot can come pick it up, right? So what I might do is attach a encoder to the conveyor belt so that I can see where it is on the belt. If there's a power cycle, it's not really that big of a deal to have to rehome that system. There's also sort of a repetitiveness aspect of a conveyor, right? It's going to just go around and round and round, right? So it's okay that I don't have absolute position information about where something is on that belt.
Well, I think I understand a lot more about encoders than I did when I walked onto this stage, so thank you.
Yeah, absolutely. Happy to do it anytime.
Oh, cool. All right.
Oh, hey, Phil.
Oh, yeah?
If you'd like to learn more about this kind of thing, you can always like and subscribe to our ES&E TV YouTube channel.
And you should probably like this video and hit the bell notification too so that you get notifications.
That's a great idea.
Awesome.